Hello from the Department of Mathematics at Aberystwyth University, overlooking the beautiful town of Aberystwyth and Cardigan Bay on the west coast of Wales. My name is Dr. Gwion Evans. I'm a mathematics lecturer here at Aberystwyth University, and I'd like to introduce you to maybe a new way of representing numbers, which turn out to be a particularly effective way of doing so. So first, well, let's recall that it's, as per usual, we can think of a real number as living on an infinite line, the real line. And as you may know, the real numbers come in various different types. And two main types I would like to focus on today are the rational numbers and the irrational numbers. So a rational number is one where you can write as a fraction, as one integer over another. So numbers such as these are dotted around the real line. However, as you also may know, these rational numbers don't cover the whole real line. In fact, the gaps they leave are, in a certain sense, more numerous than the rational numbers themselves. In other words, the so-called irrational numbers, the numbers that fill in the gaps, as it were, that can't be written as one integer over another, there are many more irrational numbers than there are rational numbers. So it's important to know how to deal with these irrational numbers. Here are a few. It's the well-known square root of 2. Here's Euler's number E, and here's another famous irrational number, pi. And maybe not quite so famous, but still rather beautiful, 3 over 2 plus a half square root 13. Okay, well, one way we can represent them is by these symbols, of course, but how on earth do we know that they appear in this order on the real line? Well, the natural thing is to consider their decimal expansions. For example, pi's decimal expansion is this. How would one actually approximate pi using just rational numbers? So the problem with this irrational number is that this pattern of decimal digits carries on forever, and I'm kind of slightly fudging the situation slightly here by saying, well, only that. It carries on forever, but I don't tell you how. And so it would be nice to be able to approximate pi by some more familiar numbers, such as the rational numbers. Well, one way we could do this is to simply truncate its decimal expansion at the 0th, the 1st, 2nd, and 3rd, 4th, 5th decimal place, as it were. These will give us rational numbers by simply, well, we can see that they are rational numbers by multiplying by an appropriate power of 10 to get the numerator, and then that appropriate power of 10 is the denominator. So if we multiply 3.1 by 10, we get 31 as the numerator, and then the denominator is 10, of course. Here I've simply simplified the fraction. 314 over 100 simplifies to 157 over 50 in its lowest terms. Okay, so that's all well and good, but are they particularly good approximations? Why focus in on powers of 10? What have powers of 10 got to do with pi? Pi is, after all, this constant of nature, almost this ratio of the diameter to the circumference. So why on earth should we use powers of 10? We could use another base, for example, in binary or ternary or hexadecimal. But again, that seems to be an arbitrary choice. So I propose a better way. So rather like its decimal expansion, we could focus in on the integer part here, 3, and then what's left over. So that would be our first way of approximating. Focus in on the integer part of pi. Now, the integer part of pi I'll denote by A0 and use this symbol, which denotes the integer part, or what's sometimes known as the floor function, which is defined simply to be the greatest integer which doesn't exceed that number pi. And then we have what's left over, the fractional part, the part that lies between 0 and 1. So, well, we know that pi is approximately 3.14159, so we can clearly see that its integer part is 3. If we go to 4, that would exceed pi, and we can easily calculate its fractional part as f0 pi minus 3. So we have pi is equal to 3 plus its fractional part f0. Okay, so what do we do then? How can we? That's all well and good. We've got the integer part 3. It's not a brilliant approximation. So, well, we can work further with this fractional part. Notice it's less than 1. And if we wanted to decompose that further, maybe we would consider, well, it's reciprocal. If it's reciprocal, it's greater than 1. And so we can repeat this process of decomposing that reciprocal into an integer part and a fractional part. Okay, so here again, this is the floor function, but now of a1 prime. We take the integer part of a1 prime, and then what's left over, which is going to be between 0 and 1. And so ultimately we'll be able to write pi as 3 plus this fractional part now we think of as 1 over a1 prime. Okay, well, a1 prime is itself the reciprocal of f0. Okay, so let's calculate what a1 prime is. It's approximately 7.06251. You simply take the fact that f0 is pi minus 3 and take its reciprocal. Use a calculator if you like, and we find that it's approximately this value. So we can clearly see that the integer part is 7, and so we can write pi as 3 plus 1 over 7 plus this new fractional part, which is again between 0 and 1. So we can repeat this process. We can think, okay, this fractional part, take its reciprocal, that would be greater than 1, so we can decompose it further into its integer part plus some new fractional part, f2 say. And so we can say, well, a1 prime is 7 plus now this 1 over a2 prime, and we're going to decompose a2 prime further. Well, again, calculating based on the fact that f1 is, well, a1 prime minus its integer part, and then we take its reciprocal. Use the calculator to calculate that as 15.99659 approximately, and so we see its integer part is 15. So we can combine that with what we found earlier and see that pi is 3 plus 1 over 7 plus 1 over 15 plus some other little bit, this new fractional part f2. Again, this is less than 1, and so we can take its reciprocal, repeat the process, integer part of now a3 prime, which we calculate to be, well, a3 prime is approximately a little bit over 1, and so its integer part is 1, and we can write pi now is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus some small bit. Again, that's the key point. These fractional parts are relatively small, so what we can do is we can ignore that fractional part at each stage and come up with an approximation by a rational number. So here we go. I'm just simply ignoring the f0 to get our 0th approximate of pi, which is not good, but it's a start. It's 3. If we go one step further, but ignore f1, this the first fractional part, as it were, we get 3 plus a 7th, which turns out to be 22 sevenths, which is a rather famous approximation of pi. Another step further, and a further step again that we made, now ignoring the fractional part of this last stage and simplifying this to a single fraction, we get 355 over 113. This turns out to be an extremely good approximation of pi. Well, how good? Well, here's again the decimal expansion of pi. I've attempted to write it all now, but run out of space. It carries on, of course, forever to the right. if I write the 0th approximation, which is the integer part 3, as a decimal, I would write this as 3.0 recurring. Not a terribly good approximation, but we see that the approximations get better as we increase the number of stages, until we get to 355, 113, and see that's correct to 6 decimal places, which is pretty impressive given that 355, 113 are not all that big, certainly in comparison with the decimal truncation numbers of numerator and denominator, which, okay, admittedly simplify to 392,699 over 125,000, but still, those numerators and denominators are pretty big compared with 355, 113. In particular, that denominator is pretty big. And indeed, not only are they both correct to 6 decimal places, but this new approximation is actually quite a bit better than the decimal truncation. We see that the difference, its distance to pi, as it were, is this much. It's less than 2.7 times 10 to the minus 7, whereas the other one is greater than 6.5 times 10 to the minus 7. And here we see, sort of visually, we see that how the approximations relate to this pi value, which is this red line here. So this is the first approximation, 22 over 7. On this scale, it looks quite far away, but then the second one doesn't look so far away, and then after that, third and onwards are pretty much bang on the line in this scale. Let's zoom in a little bit then, and see, well, actually that second approximation in this scale is not so great, but then still the third onwards is pretty good. It's bang on the line, more or less. As we zoom in further, we see, well, actually that third approximation overshoots the value of pi here down on this red line. But then the fourth and the fifth again seem to be on the line, even at this small scale. So here we're at 3.141592, and then the 7th decimal digit is given on this scale here. And then, but if we zoom in further, we see actually they're not quite on the line. 4 undershoots the value of pi, and then the 5th one overshoots it, the 6th one undershoots it, 7th one, 8th one, and so forth. So we seem to be going over and then under, over and under. That's rather curious. However, they do tend to, it seems like they tend towards this value of pi. They get closer and closer to the red line. Okay, well, we did it for pi, why not do it for square root of 2? Again, same procedure, integer part plus fractional part. And now, actually, it turns out for pi, we needed a calculator really to have a reasonable attempt at doing this. But for square root of 2, we don't really need a calculator because we can use its algebraic properties. We can use the fact that the square root of 2 is when you square it, you get 2. And so if I sandwich 2 between the next its adjacent square numbers, as it were, 1 and 4, from this inequality we can see, well, if we take square roots, the square root of 2 lies between 1 and 2. Now, of course, we kind of knew that. We know that square root of 2, decimal expansion, 1.141. Sorry, 1.414. But the point being is that we don't really need to know that. We can work it out algebraically. And it pays dividends actually. So because when we do this, we see, well, first of all, the integer part must be 1, okay, and then the fractional part is, well, square root of 2 minus that 1. And we can do the same thing again. We can take its reciprocal, that's greater than 1. We can decompose its reciprocal a1 prime to integer part plus some fractional part. But now, what is a1 prime? What is the reciprocal of that fractional part? Right, we can work it out. a1 prime is 1 over the fractional part, which was a square root of 2 minus 1. And we can rationalize this, simplify it. In other words, multiply by 1, otherwise known as square root of 2 plus 1 over square root of 2 plus 1. This simplifies to square root of 2 plus 1 over 2 minus 1, which is, well, conveniently square root of 2 plus 1. And so we want to decompose this into its integer part and the fractional part. Well, we already know that the square root of 2 is between 1 and 2, and so square root of 2 plus 1 is between 2 and 3. And so its integer part is 2. So we'll put a1 is 2, and then the fractional part is, well, it's going to be square root of 2 plus 1 minus that integer part 2, which is square root of 2 minus 1. Oh, well, that rings a bell. That's exactly the same value as we had before for the zeroth fractional part, as it were. Well, that seems quite convenient, because now we can say, well, square root of 2 is integer part 1 plus fractional part f0. f0 can be thought of as 1 over a1 prime, which we can decompose as 2, this integer part, plus this fractional part f1, which turns out to be exactly the same as f0. So we can write 2 plus f0. Well, once we realise that, we've done all the work already. And we can write f0 as 1 over a1 prime. We've already decomposed a1 prime to 2 plus f0, and we can repeat this process. And you can see this 2 must therefore repeat. So let's, again, approximate square root of 2 by forgetting these fractional parts. And here are the approximations we get. We get 1 as our zeroth approximation, then 1 plus a half, which is 3 halves, 1 plus 1 over 2 plus 1 over 2, which is 7/5, and 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, which is 17/12, and then finally we get 41 over 29. And then when we compare with the exact value of square root of 2, we see we have a pretty good comparison, especially with the 41 over 29. That's correct to 3 decimal places. Okay, and again, this 41 and 29 seems, well, much easier to work with, and certainly much smaller than the 1,414 over 1,000 that the decimal truncation approximation would give. Okay, so we may feel shortchanged and think, well, why think about the approximations? Why not think about the exact values? Well, we can certainly do that. We can. Of course, this process is an iterative process. There's no reason to end it. We could carry on forever. And in this way, we could get the next digit for this expansion of pi, as it were, which not obvious. But for square root of 2, I think you'd agree it is pretty obvious. The next one will be 2, and the one after that will be 2, and the ones evermore after that will be 2, and so forth forevermore. Okay, well, these expressions turn out to be very useful. They're called continued fractions. They come in 2 flavors. Finite continued fractions, when we stop, they terminate, as we did with the approximations. Or indeed, we could carry on without end in such a way. So the expressions on the right-hand side are the sort of the expressions written out in full, rather cumbersome to write it out in full. So we adopt this more succinct notation, akin to the decimal digits, as it were, but now these A0, A1s, A2s, and so forth can be integers or numbers. If we restrict them to be integers, and moreover, the A1, A2, and so forth are positive integers, which may possibly terminate or may carry on forever, then we'll say that the continued fraction is simple. And these are particularly nice to work with. They have very nice properties. So, to summarize, well, we've expressed pi as the continued fraction 3, 7, 15, 1, and then the next digit happens to be 292. But then it's 1, 1, 1, and I wonder what happens next. Does a pattern emerge there or not? Certainly emerges for square root of 2, where we have 1 and followed by 2 recurring, as it were. And I'll denote the recurring bit by a bar over the top, in analogy with what we do for decimals. Indeed, if I consider this particular rational number, 1,000 over 254, which is the number of inches in a meter, it's a particularly complicated decimal expansion. you may already know that a rational number has a periodic decimal expansion. So after a certain while, certain chunks of it will repeat forevermore. In this case, this 42 long-digit section here will repeat. But its continued fraction is much shorter. It's 39.212214. Easier to work with, in a sense. Well, it may not be such a surprise that a finite continued fraction will give rise to a rational number. It's also not so difficult to see that a rational number will always have a finite simple continued fraction representation. Actually, in two ways, and exactly two ways. One of which ends in a 1, and the other, doesn't. It's strictly greater than 1, the last term here. And they're related by the fact that, well, if the one that ends with a 1 is related to the other one by, well, we just add 1 to the previous term, as it were, and stop there rather than carrying on to the 1. Once you think about this, it's fairly straightforward to see why. What about irrational numbers then? Well, every irrational number actually can be expressed in exactly one way, but as an infinite simple continued fraction. And therein lies the difference between rational and irrational numbers. Irrational numbers have infinite continued fraction expansions, whereas rational numbers have finite simple continued fraction expansions. Similar in a way to irrational numbers have infinite decimal expansion, but which never repeats, whereas a rational number has a periodic decimal expansion. In other words, it repeats at a certain while. But this seems to be more definitely it ends, and it's sometimes difficult to know how long that period is for decimal expansion to repeat for a rational number. Also, continued fractions have lots of structure inherent in them, very, very well behaved and regular. So in particular, if you consider a finite continued fraction, you can think of it as a fraction in its lowest terms, Pn over Qn, and the Pn's and Qn's have a nice recurrence relation with the terms of the continued fraction. This we will investigate further in the live session. For those of you who have come across matrices before, you may be interested to know we can write this in matrix form, and it turns out to be fruitful in doing so, and there's many beautiful connections with other areas of mathematics as a consequence. And just some terminology, if we have a simple continued fraction expansion for a number x, if we end it at the nth term, we'll call the resulting fraction the nth convergent of x. And as we saw for pi, we see that the first and second and third convergent, as it were, got fourth and so on, they get closer and closer to the value of pi. Does that always hold? So far from being mere curiosity, revealing maybe some hidden patterns, for example, in square root of 2, there was no apparent pattern in the decimal expansion, but there was a very obvious pattern in its continued fraction expansion. It turns out that continued fractions turn out to be a very useful theoretical tool in many areas of mathematics, in particular in number theory, but not exclusive to number theory. They are, in a sense, the best rational approximations of irrational numbers, or they give the best rational approximations of irrational numbers in the kind of way that we saw it seen just now. They also can be used to solve some Diophantine equations that have integer value solutions, where we restrict the solutions to have integer values. And curiously, they allow us to classify what are known as rational tangles. So if you imagine some strings and tying them together, as it were, or entangling them together into a tangled mess, we can actually make sense, systematic, we can classify these tangles in a systematic way using continued fractions. And that's quite fortunate for the biologists, because those are the kinds of tools that are necessary to understand protein DNA complexes which tangle in amongst themselves. They're also used in the theory of music, in particular in coming up with new musical scales and tuning. This goes back to the idea of the Pythagorean idea of harmony, as it were, and that intervals should come in whole number ratios, as it were. Okay, so what to do next? Well, lots to do. Why not compute the continued fractions of some other numbers? Here are some suggestions. We mentioned E, Euler's number, with the base of the natural logarithm. Why not compute the continued fraction of E, maybe using a calculator, or indeed the square root of E? What about square roots of other numbers, square root of 3? And this other curious number I mentioned, half times 3 plus square root of 13. What about some trigonometric values, as it were? What about tan over 1 over k? Have a go at, use a calculator and follow the algorithm or the procedure I did for pi and square root of 2, if you like. Why not then compute their convergence? You can use the last theorem to compute the Pn and the Qn. How close are they, those fractions, to the actual values? And we can reverse engineer this. You'd actually start with a continued fraction, a sequence of numbers, integers, say, positive integers, and then think, well, what do they represent? You could, the finite ones will represent rational numbers. What about infinite ones? Maybe with some that follow a particularly nice regular pattern. Actually, what can be said about infinite, what more can be said about infinite continued fractions? But actually, does it make sense? If I give you just a sequence of positive integers, and say, well, this is the continued fraction expansion of something, is that true? Do they always represent a real number? And if so, well, which type? And if not, well, which sequences of numbers will represent real numbers and which one don't? So we saw the square root of 2 had a particularly regular pattern. The 2 repeated. It was a periodic continued fraction. What about others? What do they have in common with square root of 2, if anything? And why not try and think about proving some of the theorems we've discussed? For example, the one about the convergence. We had this nice recurrence relation that held for all n. And think about what type of method of proof you'd use to prove that those relations hold for all n. And I mentioned that the convergence of continued fractions are the best rational approximations of an irrational number. Well, in what sense are they the best? So I will attempt to justify that claim in the live session. I hope you can make it, and I look forward to exploring these continued fractions with you further. Thank you for listening.